Alright, I'm going to run through the FRQs for the Unit 5 exam. I'll be honest, I think these are some of the easiest FRQs that I've ever had on a test, so hopefully that's any comfort to you guys. So for the first one, you will need a calculator. I know that doesn't show that on your paper, but yeah, this one definitely requires a calculator. So let f be a twice differentiable function such that f prime of 2 is equal to 0. So the derivative at x equals 2 is 0. The second derivative of f is given right here for 0 to 6. On what open intervals from 0 to 6 is the graph of f going to be concave down? So let me go ahead and actually graph f prime of 2 that we have right here. We're just going to graph it as f of x. Don't graph it as f double prime. So we're just going to graph this as f of x. And that's going to be equal to x squared. And then e raised to the 2 minus x. 2 minus x. Whoops, I need to put that in parentheses. 2 minus x. And then it was minus 1. Then minus 1. Okay, so this is the second derivative. We're trying to figure out where it is concave down, so on what open intervals from 0 to 6. Now, if you do want to restrict that right there, so we can go in here, if we use these right here, and make an inequality such that 0 is less than or equal to x is less than or equal to 6 right here. Now we have it just a little bit that much more easier. And I'm going to look at these zeros right here. So honestly, it's easier to kind of give a reason for your answer first. So the graph of f is concave down. Well, if you can give the definition, that will be the reason for your answer. So f is concave down when the second derivative is less than 0, or when it's negative. So there's your reason, and now we just got to give the answer. And so looking at this graph right here, it's got to be between 0 and 0.464. So I'll do 0.464, and I'll do between 5.357 and 6 right there. Cool. And I can double check that. I have a key for this right here. I can double check that. I'll check that as we go. But that should be it right there. It's really all that we need to do right there. So we have our answer and we have our justification. And the justification is always just going to be the definition of concavity pretty much most of the time. All right. So does f have a relative minimum, maximum, or neither at x equals 2? So I think here we're going to be using the second derivative test. We know that f prime of 2 is equal to 0. So I'm going to state that. So f prime of 2 is equal to 0. So there is a critical point. So there is a critical point at x equals 2. Okay. There's a critical point at x equals 2. And then let's go ahead and look at the graph. And at x equals 2, you can see, now it's kind of confusing. It also appears that there's a critical point for f double prime at x equals 2, but that doesn't mean anything. But so it's not a maximum here for f. That is not. Maybe for f double prime, not for f. But because f double prime of 2 is positive, you can see that from this graph that the second derivative is positive. Okay, I'll state this right here. I'll say and f double prime of 2 is positive. So this is the second derivative test right here. So we can basically just say that because of these two things right here, f And one second, let me make sure that this English is making sense. So f prime of 2 is equal to 0, so there's a critical point at x equals 2, and f double prime 2 is positive. So so f must have a relative. Okay, well, so because f double prime is positive, that means the curve is concave up, and because it's a critical point right there, that means it has to be a minimum. So f must have a relative minimum. Okay, I think that's all we need to include. I actually have the key pulled up here. So for part B right here, yep, gotta have second derivative test. I don't think you have to state that the second derivative test, but I think that is the second derivative test. I don't think you have to state that you're using it, but yep, relative minimum, because f prime of 2 is 0 and f double prime of 2 is positive. Okay, and I'm gonna check for part A. Yep. Yep. Okay, yeah, it looks like I'm good so far. All right. For 18, use the mean value theorem on the closed interval from 2 to 4 to show that f prime of 4 cannot equal 8.5. So, sorry, I am having a runny nose right now. So we're going to use the mean value theorem on f prime because we have f double prime here. So kind of weird, but so the mean value theorem states that at some point the average rate of change must equal the instantaneous rate of change. And so we're going to show that f prime of 4 minus f prime of 2. So this interval with what we know about f prime of 4, right, or what we're trying to prove about f prime of 4, all over 4 minus 2. So here is the formula for the average rate of change on the graph of f prime. And at some point we're saying that this right here, I'll put, if we're using the mean value theorem, we're trying to prove that, I guess, that this will equal, that this must equal f double prime of 4. Not double prime of 4, but double prime of x. So the mean value theorem says that the average rate of change will equal the instantaneous rate of change. But we're trying to prove that this, that f prime of 4 cannot equal 8.5. Okay, but what we do know about this right here, I'm also just going to erase this. Okay, what I do know is that f prime of 2 is 0. So this right here will be f prime of 4. Actually, let's just plug in 8.5, I guess. 8.5 minus 0 over 2. And that, of course, is going to be equal to 4.25, right? And we're going to show here that this does not equal the second derivative of x. So I can show that in the graph right here. So I'm just going to graph, or I'm going to do 8.5, right? 8.5 divided by 2. I'm going to first make sure that that's equal to 4.25. Yep. And then I'm going to do y equals. Okay, so here is this value right here, 4.25, which we have up here, and here's the graph of f double prime. They never equal each other right here. Never equal each other. They might equal each other, so let's say that you take away the domain from this, it might equal each other on a different interval, but right now on the interval from 2 to 4, if f double prime of 4 equals 8.5, then this won't equal the second derivative. So I'll just say, let's see right here. So we have that work right there. What do I need to state? I guess I need to state the conditions of the mean value theorem. So f prime is differentiable. It's continuous and differentiable. It's continuous and differentiable, okay? So the mean value theorem does apply. So the mean value theorem, I'll just say MVT, so mean value theorem conditions are met. Okay. So there must be, so let's see right here. So there must be a value in this interval from 2 to 4 where the average rate of change equals the instantaneous rate of change. There must be a value, okay? However, because we checked this 8.5 right here, and they don't give you the same value, it's not possible for f prime of 4 to equal 8.5. So basically, all we're trying to say is that 8.5 is an incorrect value of f prime of 4. That's all we're really saying right here. So f prime is continuous and differential, so the mean value conditions are met. So there must be some value, there must be a time where the average rate of change will equal f double prime of 2, but it's not going to be when f prime of 4 equals 8.5. Trying to think of a way to say that that's kind of clean. F prime is continuous and differential, so the mean value theorem conditions are met. I guess you can say, but f prime of 4 cannot equal 8.5. Okay. I think this right here combined with this statement right here is all that you need. I think that's fine. Probably even more than we need. But yeah, we'll call that good. All right, so for 19, does the graph of f have a point of inflection at x equals 5? So if there is a point of inflection at x equals 5, then f double prime has to be changing from positive to negative. So let's go in here. You can see that it does change signs, but it doesn't change signs at x equals 5. So no, because f double prime does not change signs at x equals 5. Cool. I think that's all we gotta do for that right there. We're gonna call it good. For FRQ 2, the number of fish in a small bay is modeled by the function f defined here. Whoops. That should be f. Whatever. All right, and t is measured in days from 0 to 8. So for 20, using correct units, interpret the meaning of f prime of 4 equals negative 30 in context of the problem. So f prime of 4 equal to negative 30. So f prime of 4 it means at t equals 4 days. I'm just going to say it like that. T equals 4 days. The number of fish. The number of fish in the bay is decreasing. It's decreasing at a rate of 30 fish per day. I think that's all I got to do. So I got a time. I don't know why I say a, at. So at, I also specify the function. So what is the function? The function is the number of fish. And I'm saying that it is decreasing at a rate of 30. You can also say that it's changing at a rate of negative 30 fish per day or something like that. But I think this is a good way to interpret that right there. And I have the correct context, correct units, right? 21. Based on the model, what is the absolute minimum number of fish in the bay over the time from 0 to 8? Must show work with the candidates test. So this is technically no calculator required on here, so I am going to expect you guys to show your work without a calculator, although you will be able to use one. So what we're going to do, so we're basically giveaway, we're going to be using the candidates test. So I need to find critical points. So f prime of t, we'll find the derivative. So going up here, because this is a multiple or a constant, I can use the constant multiple rule, which is just take the constant and that'll multiply by the derivative here. So that's going to be 3t squared minus 24t plus 45. I'm going to set that equal to 0. I'm going to factor a bit, so I can bring out a 3, so that's going to be 30 out here. Then I'll get t squared minus 8t plus 15. And then I'm going to find what makes t equal to 0. So that's going to be at t, sorry, I'm going to factor it first. So t minus 3 and t minus 5, I believe. So at t equals 3 and at t equals 5. Okay, and then we'll have our number line. So, no, we don't need a number line. This is the candidates test. We need a table. So we'll make a table. Okay, and table is good for work here. That should be fine. We're just going to plug in the endpoints. So candidates test. We're going to plug in the endpoints, 0 and 8, and our critical points, 3 and 5. Okay, so this is where I really don't care if you guys use a calculator to find the values. That's probably just what I'm going to do. I'm just going to take these and I'm going to plug them into the function because I don't want to do that by hand. So, and it's also kind of just good to kind of, I guess you, I don't know, I'm not going to say that, never mind. But yeah, plug those in to a calculator, make it easy. You can plug them into Desmos, you can plug them into a scientific calculator or whatever you want, but I guess I'll plug them into my calculator that I have right here. It takes longer than using Desmos, but whatever. Okay, so I've got... Well, we can plug in 0 first of all. Plugging in 0 is not bad. That's going to be 1,000. So it's going to be 1,000. All right, we can plug in 3. Okay, I'm plugging them into the function. So that's going to be 10. Then we're going to have x squared. No, x to the third. X to the third. And then we're going to have minus 12 x squared plus 45x plus 100. And at t equals 3, I have 1540. Okay, now I'm going to do 5 towards x, and I get 1500. And then for 8, I get 2040. All right, so it seems that the minimum is going to be at x equals 0. So what is the absolute minimum number of fish in the bay? 1,000 is the absolute minimum number of fish in the bay. From t equals 0 to t equals 8 days. As far as your justification, I'm just going to say that your work here and here is justification. So basically just finding the critical points that you have right here and testing the critical points into the function and seeing that here we have the minimum value. So that's going to be your justification. For 22, for what values of t from 0 to 8 is the rate of change of the number of fish in the bay decreasing? So this is actually kind of tricky language right here. So the rate of change from what values from 0 to 8 is the rate of change of the number of fish decreasing. So it's not saying when the number of fish is decreasing. So, oh my gosh, my allergy is so bad right now. It's not saying that, when, for what values of t is the number of fish decreasing, that would be referring to the derivative. But we want to know when the rate of change of the number of fish is decreasing. So basically what we're trying to find is when f double prime of t is less than 0. That's what we want. We want when the second derivative is 0. So I'm going to find the second derivative of t. Oh, sorry. I'm going to go up here and do that right here. So I'm going to take the 30, and then that's going to become 2t minus 8. I'm going to set that equal to 0. So 2t is going to be equal to 8. So when t is equal to 4, that's when f double prime is going to be 0. And then I'm just going to double check and see when this is positive or negative. So I know that it's going to be 0 at 4. So let's say I plug in values to the left. So if I plug in 0 back into the second derivative, so we're going to get 0, 30 times negative 8. That's going to be, so f double prime of t will be less than 0. If I plug in any values greater than 4, say like 5, that's going to be 10 minus 8. It's going to be 2. 2 times 30 is going to be positive 60. So the second derivative is going to be positive. So I guess I'm not going to say so. Is the rate of change of the number of fish in the bay for what values? So for values, we'll say this right here. 0 is less than, t is less than 4. You could even just say it like between values of, so between t equals 0 and t equals 4. The rate of change, of the number of fish in the bay is decreasing. Because f double prime of t is less than 0. Okay, I think that should be good enough right there. Cool. For 23, for what values of t, for values between t and 8, the number of pelicans, so we're introducing something else, the number of pelicans flying near the bay is modeled by the differentiable function p, where p is the number of is a function of the number of fish in the bay. So that's important right there. Based on the models, write an expression for the rate of change of the number of pelicans flying near the bay at t equals c. So first of all, we're going to write an expression for the function of p. So what is the function of p going to be? They don't really give us much, but they do say this right here, and that is p is a function of the number of fish in the bay. So it's kind of like y is a function of x, or velocity is a function of time, or something like that right here. Or like right here, f is a function of time. F of t, it's a function of the number of days. Well, p is a function of the number of fish. So p of f of t. This is the definition for the number of pelicans. So the number of pelicans flying near the bay is modeled by this function right here. Okay, so we're going to write an expression for the rate of change of the number of pelicans in the bay. So I'm going to take the derivative of this expression right here, and that's going to give me p prime of f of t times by f prime of t, which is just the chain rule. We just got the chain rule. And then what we're going to do is plug in c. So p prime of f of c times by f prime of c, which is, well, I'm doing that because we're trying to find at t equals c. And then what we can do is we can just take these functions right here, plug in c, and plug in c, and we can use those in place of this right here. So a fully expanded out, really explicit definition would be that right there. So p prime of 10 c to the third minus 12 c squared plus 45c plus 100 or 1000, what was it? Plus 100. Okay? Times by f prime of c. And f prime of c would be this right here, so times by 10 of 3c squared minus 24c plus 45. And that's all I would do right there. So we've got p prime of f of c times by f prime of c. So there you go. That should do it right there. Kind of a weird one, but all right, there you go. Good luck with your studies, and yeah.